slide.
Oh, the screen, but not the slides?
I see this. Okay, now I see the slides. Yeah. There is 1 hour allocated to your talk. Let's say that you talk for about 45, 50 minutes, and then we have times for questions. Is that okay?
Okay, it's perfect. It's perfect. Okay, so as I was saying, thank you very much for the invitation. I'm speaking from Paris, so where it's midnight actually, so what I'll try to give you is a little overview of some work that we have done on rogue waves using large deviation theory, and I'll also, briefly discuss other topics, including tsunami, and in fact, anomalous wave past a step. And this is joint work with Tobias Grafke, who was a postdoc at Courant at the time, is known in Warwick, Giovanni De Mattis, who is a postdoc in RPI, Miguel Honorato, who is in Italy, faculty, Shanine Tong was a student, George Stader was my colleague at Courant, and Di Chi was a postdoc at Courant, and he's now in upstate New York. Okay, so what are rogue waves? Well, they are certain very high, big waves that essentially come out of nowhere, and have been known to be dangerous for ships and other structure on the ocean. The definition by oceanographer is that the crest-to-trough height h needs to exceed twice the significant wave height hs, which is itself 4 times the standard deviation of the surface elevation. Okay, and so we're going to be discussing about them. The mechanism is not yet fully understood, and the first few slides I'm going to give you are just slides that show you a few of these waves that were observed in the ocean. So the first slide that you see here are 2 pictures that were taken. One on the left was taken by the chief engineer on a tanker in 1997. It's not completely clear. It was a fairly rough sea, right? The rougher the sea, the bigger the rogue wave, since it's needs to be bigger than its surrounding. It's a little bit difficult to tell what was the height of this wave, but it submerged the deck, and the deck is about 25 meters above sea level, so it was a pretty big wave. The other picture is a picture that was taken by an oceanographer, Mitsuyasu, who spent, I think, a decade or even more on boats to actually take pictures and observe the sea. And what you see in the background there, this sort of mountain that's moving, it's pretty far, but actually pretty big, is also a rogue wave that was estimated to have, an H over HS of 2.5. So this is a fairly sorry for this little delay. So let me restart. So I was explaining to you, giving you the definition of the rogue wave and explaining these 2 pictures. On the left is the one of this tanker, 25-meter high deck that was submerged by a wave during a storm, and on the right is one picture among many that was taken by Mitsuyasu, who is a Japanese oceanographer that was, going on the deck of this boat, Captain Lopen, to take pictures. That's one of these giant waves that he saw. Okay, so these are rather anecdotal evidences of rogue wave, but they are, rogue wave that they really be documented and measured, and probably the first one that was documented that way was a wave that hit a platform, an oil platform in the North Sea, the Dropner platform, January 1st of 1995. And so the picture that you see, do you see my mouse? So I can point with the mouse? I guess so. Yeah. Right? Yeah, okay. So what you see here is, the height of the platform that was recording during a storm where the sea was pretty rough overall, because you see that you had a wave which were, maybe close to 10 meters from crest to trough. But at some point, you see that the very big event occurred with a wave that had a height that was almost 26 meters that hit the platform, and then it disappeared. Okay, came from nowhere and just went like that. And since then, many other recording of waves like that have been observed. On the right here, you see 2 pictures. The one on top is just a zoom on the one on the left, which show you again the Dropner wave. The other one is a similar wave. So it's a rogue wave that hit another platform about a decade later. It's called the Andrea wave. And the only thing that I want you to notice at this point is that these two waves had very similar features, in the sense that they were, completely different. But if you see the temporal development, they seem to be quite reproducible in a way, in the way they occur. Okay, and so one possible scenario, and that's the one that I'm going to be trying to explain here, though it's only part of the story, is that they are caused by nonlinear effect, which is called modulation and instability. And so what happened is that out of a background of typical, meaning much smaller random wave, you can potentially have some form of this instability that builds all the energy into one big event that come and goes. Okay, and we're going to try to explain that. Now the measurement on the sea are actually pretty scant, but what I'm going to do in the talk is discuss raw waves that were created and observed in flume experiments. So these are experiments that were done by Chapshoop and other. And so it's in a big wave tank in which at one end there is a wave maker, and at the other end there is a beach. So the wave maker is creating wave with the energy spectrum that you desire, and then these waves propagate through the tank, and you can measure the height as they propagate through the tank. And so the idea here is essentially that you're creating some random set of initial data at one end of the tank with, I'm going to explain that in a minute, with an energy spectrum which is similar to the one that is found in the sea, and then these waves propagate in one direction in the tank, and then you just see out of these random initial data, if you wish, what is created at later time. Okay, and in particular, this experiment, because they are probe all along the tank, as the advantage that if ever you detect a rogue wave hitting one of the monitoring point, right, you can actually look back at the recording and you know what was this wave as it hit the previous. So you have the temporal history, which in this case is just a length history, because you can interchange space and time using the dispersion relation of the water wave. Okay, so that's what we're going to do. Okay, so what I want to explain here is a connection with large deviation, which allows to explain, the statistics and the mechanism of these waves. And so, okay, so before I do that, just for amusement, this is a smaller tank. This is what happened when we wrote wave. It's small because it's much bigger than the surrounding. And then they did a Lego ship, and when the waves hit, that was a good wave. Put the movie because I found it funny, but also because you see that the wave was not actually created. The way it's actually doing is that you just create random initial data, and at some point something bigger than usual occur. Okay, so the way we're gonna do a model for this that I would like to analyze a little bit is by taking two components that each individually seems to be reasonable model for the system at end. So the first one is that we're going to use as a dynamical equation to model the propagation of the wave, the nonlinear Schrödinger equation. In fact, some of the calculations I'm going to show you are using a modified version of the Schrödinger equation, which is called this equation, that includes higher order term, but it's not very important. So for simplicity on the slide, I just wrote the nonlinear Schrödinger equation. So it's an equation for a complex field. And what is simply done here is essentially the real part of this field gives you the height of the sea. Okay, it's normalized so that the domain is 0, 1, but you should think about that as a large, very large domain. And so we take that as a dynamical equation. It's a deterministic dynamical system, meaning if you give it an initial condition, we just propagate this initial condition deterministically. But what we're going to do is that we're going to feed as initial condition in this equation random initial data. And the way we're going to take the random initial data is essentially by assuming that we take random initial data that are Gaussian field with an energy spectrum which is consistent with the Jones-Swap spectrum. So the Jones-Swap spectrum is this spectrum that was obtained by the Joint North Sea Wave Observation Project, who spent time in the North Sea and just made measurement to figure out what's the energy spectrum that you have in the sea for different sea conditions. And these spectrum look like this, and you know, the peaker they are, the more sharp they are, correspond in fact to a situation where the sea becomes rougher and rougher. Okay, so if I want to modify this model, what you should think about this is that the nonlinear Schrödinger equation is well suited if you have unidirectional, narrow banded wave field on the surface of a fluid of infinite depth. Okay, if so, it's not valid near the shore, and it's not valid either if it's not one directional. But these are approximations that, at least in the tank, are valid. We know that the nonlinear Schrödinger equation reproduce the data that is observed in the fluid. Okay, now, of course, in the sea or in what you have is that the Schrödinger equation, or whatever the system, is actually forced and damped. What we're going to do here, which is again consistent more to what happened in the tank, is assume that forcing and damping, which is ultimately what created the Jones-Schwab spectrum that we're going to use as an initial condition from random data, these forcing and damping occur on time scales that are very slow compared to the emergence of the rogue wave. Okay, so something has built up. We should imagine that in the nonlinear Schrödinger equation, there should be a source and a sink, but they are weak, okay, and they only act on very long time scale. Their effect would be to create the initial condition I'm going to take here. Instead of doing that by forcing and damping, I'm just going to neglect it, saying they don't matter on the time scale over which I will look at the equation, and I'm just going to include the effect by taking random initial data. Okay, and that seems to be a reasonable model to the extent that it reproduces, at least the Schrödinger equation, what is observed in the tank. And in the tank, it also reproduces exactly what's done, because in the tank, the wave maker can be thought of as creating a random initial data at one end of the tank. Okay, so once you have this dynamical system and you think about the problem this way, you can analyze, the issue of rogue wave in a fairly abstract way, which is you can think about you have your dynamical system, so you have initial condition that are random, they propagate, and then I can look at a later time, and I can simply ask myself at this time, what is the probability to observe a wave of a certain height? Okay, so if you want to, write that, I can write down abstractly the dynamical system of Schrödinger equation as this du dt is equal to some right-hand side that they be of u. There's an initial condition that is Gaussian with a certain spectrum. That's the C here, the covariance matrix of the field. Okay, and what we want to do essentially is to look at the probability that the L infinity norm, so the amplitude of the field or the amplitude of the wave themselves, is above a certain threshold z at time t. Okay, where all the randomness here come from the initial condition. If for a given initial condition, the rest here of the dynamics is deterministic. Okay, so this problem at first sight might look trivial because the initial conditions are Gaussian, but I want to insist that it actually is not trivial, because what you are looking at is the statistics of the solution at the later time t, and this solution is evolved by a nonlinear equation, and so it is actually difficult. The map between the initial condition and the observable, which is the amplitude of the field at time t, is in fact a very complicated map that you don't know explicitly. Okay, so analytical results are difficult, very few here. Of course, one thing one can do is just use brute force Monte Carlo sampling to calculate this quantity, which would amount simply to, well, numerically, what would you do? You would draw initial condition from the Gaussian, propagate them by the nonlinear Schrödinger equation, and just use this initial condition as a data set over which you verify, what's the proportion in the data set of realization in which the event is realized. The difficulty with this strategy is that it's very inefficient, especially if you look at events where you want to look at large wave, because the data set that you have, that significant shrink, the bigger z, the more unlikely it is to get one of these waves, and so the more simulation you would have to do. So what I'm going to do here is to recast the problem as an optimization problem, and in order to do that, I will use result from large deviation theory, okay, which is the essence of the work. So I don't assume that everyone in the audience is familiar with large deviation theory. So large deviation theory is something quite old at this point. I mean, it's in probabilities has become a classic in which you have limit theorem, you have the law of large number, the central limit theorem, and then the third component of this triple is the law is a large deviation principle, and that's what large deviation theory is about. It was originally the first large deviation result was obtained by Kramer, which is the black and white picture here. A Swede who was a statistician, and a big part of the theory has been developed by my colleague at Coron, Vanden. This is the other picture, and it's actually fairly easy to explain what large deviation theory is, at least in, if you leave aside all the technicality. It is the Anna-Karenine principle. It says happy family are all alike. Every unhappy family is unhappy in its own way. So if you think about this motto, right, this little phrase, the rare event is the happy family. And why are they all alike is because in order for a family to be happy, everything needs to fall into place. There's only one way for this to happen. Whereas if anything goes wrong, well, then you're unhappy. Same thing with rare events. Typically, for a rare or an extreme event to occur, everything needs to fall into place in exactly a right way for them to occur. And so that means that their pathway or the way they occur typically is dominated by the most likely, which in fact means the least unlikely scenario that you can envision, okay? If you want to go a little bit more into technicality, it's in some sense equivalent to, it's a functional equivalent of Laplace method to calculate integral. So when you calculate probabilities, you essentially are calculating integrals over a probability distribution that can sometimes live in an infinite dimensional space. If this probability distribution is fairly peaked, or if you look at things that happen in the tail, typically what happens is that when you do an integral, like in Laplace method, the integral over a set is dominated by the point where the integrand is the most likely. So if you look at an integral over A, so imagine that F here as the level set that are depicted, by the black line that are here, and that decays very quickly because what I'm integrating is the exponential of -1 over epsilon. Epsilon is small, so epsilon minus 1 is big, of F, so it decays very, very fast. Right, so if I integrate this function over the set A, which is the red region here, well, then the only point that will matter in this integral, essentially the only region where there will be a significant contribution of the integral is the red point that maximizes the function within the set. Okay, in fact, minimizes the function, maximizes the integrand. Okay, and so what large deviation theory does, in effect, is identify the point in the set. Now, in the context of a dynamical system like this, what does that amount to do? Well, it's essentially doing a minimization problem where instead of trying to do this complicated integral that you would have to do to calculate this probability, what you do is you simply find the point of maximum likelihood. So for a Gaussian, right, this maximum likelihood is actually very easy because for a Gaussian, you can write down the cost, if you wish, which is simply the density of the Gaussian, sees the covariance here, right? And so what you do, instead of integrating over this factor, you try to find the point among all the initial data which maximizes the cost given the constraint that you would like the amplitude of the field to be above z. Okay, and so instead of calculating this probability either by Monte Carlo or by doing the integral, which is one is hard, the other one is impossible even, what you would do is just you turn it into this minimization problem. Okay, this minimization problem is simpler than this, and I'll show you how to do it. It's non-trivial either. You do need to do it numerically because, well, even though the cost here is quadratic and is simple, the set over which you want to do this, the constraint set here is actually complicated, again, because the map between u0 and the solution at time t is a complicated nonlinear map, okay? But this can be done. And so, in practice, and I want to go quickly on this because I would like to focus on more the result of the theory. So you can actually do that numerically. What does that amount to do is, well, in essence, is that you need to do the optimization which is done here. In order to do that, you can use a gradient descent method. You need to be able to calculate the gradient of this objective function by including the constraint here, for example, using Lagrange multiplier. This requires typically to use an adjoint method to calculate to enforce the constraint. And on top of that, it requires to simulate the equation up to time t, which is a Schrödinger equation, to actually verify the constraint. Okay, so that's what we did, and that's what's explained here. But I'm not going to go into these details. I'm just going to give you, the result to show you what it gives. Okay, so first of all, what do you do when you do the optimization? Right, again, you're trying to find an initial condition which is special among this Gaussian field of possible initial condition, so that it creates a rare event. So if you pick a standard initial condition, there's the graph so a typical initial condition graph on the right. I'm just showing you the amplitude here. What happens is that the field is actually evolving and nothing much happened. It's as rough at any given time as it seems, at the beginning of time, which is initial condition. If, however, you optimize the initial condition in such a way that you enforce to find the initial condition that is the most likely over the Gaussian for the rare event to occur, which is to have a big wave, well then, by definition, by construction, the wave occurs. And that's what you see here. Okay, deterministic evolution from this initial condition. We only see here the amplitude of the field, so it's actually more complicated than that. Okay, and so if you do this optimization, right, you can actually calculate now not only the most likely way the wave will occur according to the theory of large deviation, but also its probability. Okay, and you can compare that with result from brute force Monte Carlo just to validate things. And so what the graph at the left are showing you is that the dots are essentially results that are done using brute force Monte Carlo, which is costly, and the lines are superposed to that, the result that you obtain just by doing the large deviation. So I have not proven that there is a large deviation principle that applies here, but this is kind of the empirical evidence that it does, because when you do when you actually apply it, you realize that it actually captures the probability. Maybe more interesting is what happened on the right. What you see here is the development of a wave. So this is not the amplitude, it's really just the height of the sea from an initial condition. So we ask, what is the most likely initial condition to create a wave of certain height? And it turned out that this is the initial condition. This is the black curve, according to the theory of large deviation, that develops in time to create this wave that is the rogue wave. Okay, it's actually a fairly small rogue wave because we wanted to verify the result of the large deviation theory and compare it with Monte Carlo. So independently of the optimization that you can do with large deviation, you can also simply do brute force Monte Carlo simulation and then look. So this is like a search at random, but you search for this big wave, and then once you observe big wave, which are only constrained or having a certain height, you can actually look at their shape. Okay, and one way to do that is that you center all the wave to put them in at the right place, because otherwise they can happen anywhere, and then you average them to see what is the mean shape of the wave, and you look at the fluctuation around it. And the mean shape of the wave is the blue curve that is behind the black one, and this blue cloud is just the one standard deviation around it on the data. And so what this tells you is that the optimization of large deviation does capture exactly what is happening in the Monte Carlo, meaning that when you do the Monte Carlo, in principle, a wave of this height could occur in many different ways. But like our happy families at the beginning of the talk, 2 slides before, they only happen in one way in practice, effectively, And that way is the one that is predicted by large deviation, which is that you see the shape of the wave that's superimposed perfectly. Okay. Now, why is this interesting? Okay, so is that, okay, this is, I mean, this in some sense here is just an empirical verification that the large deviation theory applies for the nonlinear Schrödinger equation. But it's a bit of an internal consistency test because there is no data except the one that are coming from the, you know, the equation itself. These graphs are perhaps a little bit more interesting because these are the graphs where you do the same thing, but now you take the data from the tank. And if you take the data from the tank, what you see is that it's essentially the same story. So you can calculate, given, you know, the initial conditions that are created in the tank for 3 different conditions of the sea, if you wish, you can do the optimization to look at what are the I wave that you should have, how the rogue wave occur. And then you can compare that with the data from the tank that you filter in the same way as before. You look at all the waves that go over a certain height, you center them, you average, and then you look at the, you know, the standard deviation around that. And these are, again, these clouds and the color pictures that you see around them. And you see that once again, the large deviation result captures almost perfectly the mechanism of the wave, at least where the waves occur. I mean, this is a random bath, so there's more noise, but where the wave occur, you see that there's almost exact superposition between the prediction from large deviation, the mean that in the tank, and in fact, you see that there is no fluctuation around the mean because there is the cloud is actually the red cloud, or the green or the blue is actually superimposed. Okay, so in some sense, this is telling you that the large deviation formally building on and using the nonlinear Schrödinger equation in random initial data actually captures the mechanism of the rogue wave in the fluid. Okay, you can then try to do some analysis, and you perhaps some people in the audience know that there's essentially 2 camps in rogue wave theory. Some that says that in fact it's just superposition of Gaussian bath, and this is this theory of quasi-determinism that's been around for quite a while. And others that say, well, no, actually it's all modulation instability. So what you can do here is you can actually look, and again, this is in the experiment, you can look at how do the wave look in different sea conditions, coming from a sea that is very quiet, that's on the left here, to something which is very, you know, much rougher sea. And what you see is that the rogue wave, this is a contour plot of this wave in space-time, change. So these are the result from the large deviation theory that again I created with the experiment in the center, and you see that the result from the experiment change from. So the nature of the rogue wave changes as the sea become rougher. And in fact, the one on the left is something that you can explain quite easily, because this is, if the sea is sufficiently weak, you don't need to take into account, you can linearize the Schrödinger equation. If you linearize the Schrödinger equation, the Gaussian initial condition is preserved, and so you can just look at how do you create a rogue wave in the initial condition. That's that. And indeed, for weakly nonlinear situation, this is what you observe. But this stops being valid if the nonlinearity becomes stronger and stronger, and then at some point you end up having something that you can compare with something else, namely the peregrine soliton. So let me just explain that in 2 minutes. So one reason why people believe that, you know, modulation instability could be the cause of rogue wave is that you in nonlinear Schrödinger equation you can compute certain soliton. And the peregrine soliton is one specific soliton that has a property that it is localized, it's shown also up here, it's localized both in space and time. So it seems like a good candidate for a rogue wave. It's a strange solution if you want to apply it to rogue wave, because you can create a peregrine soliton of arbitrary height. It's just one solution with adjustable parameters. You don't have any probability. It's a solution that you can adjust. It simply happens that when we do the calculation, without putting as an input that anything about the peregrine soliton, what we see is that the result from large deviation produces a wave that agrees with the peregrine soliton or can be fitted, like the peregrine soliton can be fitted to it in the core of the where the wave occur. And this is only true if you have strong nonlinearity and not in the weakly nonlinear regime. Okay, the peregrine soliton, let me insist on this, has no probability. We are able to calculate the probability, and this is emerging. And also you see that this agreement is only true in the core. The peregrine soliton has strange tail where the sea needs to be very high that are not observed, and it also decay in a strange way at initial time. So this is not the same initial condition that the one that creates the peregrine soliton. It's just that if you look at one time slice where the wave occur, it looks like the peregrine soliton. Okay, and so what this shows, in fact, is that the debate between is it modulation on instability or is it just superposition of linear waves is, in fact, well, both camps are right. If you are looking at smaller waves that occur in a regime where essentially you can linearize the dynamics, well, it's just a superposition of Gaussian waves. But if you go in the strongly nonlinear regime, then it's something different. And the experiment in the tank tell you that this actually is something that it can in fact be observed. I mean, so that it's the nonlinear regime is accessible in the experiment. Whether it's accessible in the sea, that I don't know. Okay, okay. So since I started late, I'm going to try to shorten. This is the way these waves occur. If you want to see them again with the comparison with the peregrine soliton, this is like, you know, the initial condition, and how it develops into this wave in the simulation in the Monte Carlo. Okay, and again, this is right. This is the wave, and then it goes. And it looks like it's more oscillatory than in the experiment, or in the, but in fact it's matched. Okay. Okay, so oh, sorry, what is that? Okay, so I will maybe skip this in the interest of time, because I don't want to take too much of your time since we stayed late. I don't want to be in favor. I'm going to simply maybe go, you know, towards the end of my talk already and tell you that, well, what we saw here is that there is a way in certain cases or set of mathematical tools that seems to be applicable in certain situations where you have dynamical system with random component, initial conditions, say, but could be something else. And then what you want to show is you want to try to compute the statistics over this initial condition of certain extreme events. I did it for the rogue wave, but there's other waves or other mechanisms that you can apply. So here's two examples. One is that we did a similar kind of analysis for tsunami. These are really baby tsunami because they are one-dimensional, and they are created. So this is a model in which you model the surface of the sea by the shallow water wave equation. So it's a different regime. It's on planetary scale now, and you imagine that tsunami are created by earthquake. And what does that mean is that the earthquake is actually changing the sea floor in one go, which changed the surface elevation above it because it just lift everything up. And then that's an initial condition where no, the sea is not flat, if you wish. It has a little, and then this guy propagates. Okay, and so you can do exactly the same thing here, which is that in this model you can make a model for the seafloor elevation random, depending on the model for random earthquake, and then this creates random wave or random tsunami. And what you can ask is, what's the probability of having a tsunami of a certain height, roughly speaking? And so you can actually do that by doing exactly the same thing. And again, you can show that the large deviation result is actually capturing in this model fairly accurately the probability of observing high tsunami. Okay, that's actually the MC sampling is the blue curve, and then the result from the large deviation, I'm not sure actually I have shown it here. What was done here is to use the result of large deviation as a way to do important sampling. So to bias the Monte Carlo to make it more efficient so that you can actually go and look at the tail, which now gives you the probability of very high tsunami. That would be very rare, but not that rare actually. This, you know, so on decadal time scale or centuries, this could actually have an importance. I mean, as I explained, this is such a baby model of tsunami that I don't want to make any claim about, but the framework could be applicable, okay? And then these are these tsunamis that are propagating there that you see, or right in this model. And then, you know, there is another type of wave that we have recently analyzed, and this is with DG. The previous example was with Gorg Stadler and Shannon Tong, which is this is again experimental data, where these are experiments by Nick Moore, and what he did. So what the experiment is that you create it's the same similar tank experiment, except that it's a much more shallow tank. And the way the wave is actually, what's happening in the tank is that there's a step that is put at the bottom. And this has a feature that if you look at the statistics of the height elevation, so you create a wave elevation that's essentially Gaussian on this side. This is what's happening here. When the wave passes the step, the statistics of the wave height dramatically change. It becomes skewed. And the tail of high event increase, whereas the tail of negative, so you know you get more high waves than abnormally high wave on that side. And so these were experimental data. Andy Maida and Dichi with Nick Moore developed a model which is based on the truncated KOZWaves de Vries equation, which is a good equation for this condition, again for the wave, the amplitude here, and showed that you can get reasonable agreement between, by looking at the simulation of this equation, again with random initial data, between the statistics before and after the step. You should think about the statistics of the wave before the steps as being the initial condition, and then you look at what happened after the step, and you see that there's a reasonable agreement. And in this problem, you can again do exactly the same thing, which is that if you want to understand what these waves are, you can, in principle, do an optimization where you look at the most likely way a wave a certain height is created among these initial data. And if you do that, you see that, again, the large deviation prediction captures very well the decay of the probability, okay? And you can do something else, which is that you can again then look at, you know, what is a typical event, a rogue wave, by which you have a solution that is either abnormally high or abnormally low, and look at the time development in space of this, right? And again, you can do, you know, the little test that I've shown you in the previous case, which in this case even work even better, which is that you can compare the prediction from the large deviation from what is happening in in this case. This was not comparison with experiment. This is comparison with the numerical simulation with the KOZWaves de Vries equation. But you see that there is perfect agreement between the prediction of large deviation and what you obtain by Monte Carlo simulation. Okay, and I think so. These are a few references for the work that I just presented. And I think I will leave it at that to not take too much of your time and try to remain more or less on schedule with the rest of the conference. Thank you.
Thank you very much, Eric. We have about 30 minutes for questions. So anyone has got a question for Eric? Amin?